and here my project, I will come to geometry. If I right click on geometry, I will find out that I can either use Space Claim and also Design Modeler to create my geometry. By default, it takes Space Claim, but I want to use Design Modeler for this problem since the previous video also uses Design Modeler. So I will open Design Modeler. Now, here's another thing that I will have to do in order to use ANSYS Fluent. And the thing is that by default, this software only uses 2D and 3D geometries. So it wouldn't be possible to model a 1D object or body. I can do that though in my own code, in the one that you're also going to develop. But in order to overcome that issue, we will simply create a 3D geometry and then we will mesh it in such a way that we only have one element on the YZ plane. And then the discretization of the addition of more elements only happens on the X direction. So I will come to YX plane, so it would be this plane, and in this plane I want to sketch or draw a rectangle. So my rectangle will be, no, let me come back again to XY. I need this axis, XY. And I will sketch a rectangle that will start here and it'll prolong like this. And I will give some dimensions to this. Dimensions, I can give horizontal or vertical, or simply if I pick general, it'll pick the right kind of dimension. So if I click here, it'll create some new variable equal to h1. Now this h1 is 51.176 meters. I can make it 1 meter because we want x to go from 0 to 1. So this will be 1. And I can also create a new dimension for this vertical line. And this, I will make it, for this problem, let's create 20 elements. So if I have 20 elements along the x-axis, it means that my delta x will be equal to 5 centimeters. And I will use the same 5 centimeters for the height. So that would be 0.00, I'm sorry, 0.05. Yeah. Okay, and I want to extrude this the same 5 centimeters. So after I have defined the dimensions, I will come to modeling, create, extrude. And I want to extrude this sketch, so I will select it and then click on apply. And the depth of extrusion will be 0.05. And now I can click on generate and it will create my 3D geometry. Okay, so I'm gonna save this project so I don't lose it. If anything happens, I have here save project. And I will save it simply on my desktop so I can find it quickly in the future. And I'll call it project 1D heat transfer and steady heat transfer. Save. Okay, so now I can come to model, right click, edit. It will take some time to load, so we have to be patient. Okay. Okay, so now I have my geometry imported into this window. So I will start checking that I have everything in place. So I have here geometry imports, that's fine geometry. Here solid. My solid has structural steel as material. So I'm gonna click here and I will see the ones that I have available. So I have structural steel, and if you recall, I also added aluminum and we created my material. So I'm gonna pick my material. Now it's defined of my material. Now material is there. These are the properties of my material. I only have density, thermal conductivity, and specific capacity. Now, if I go to structural steel or aluminum, I will see that I have much more information, like Young's modulus, Poisson's ratio. But these kind of parameters or variables aren't really necessary for our simulation. So I have simply created the most essential and the ones that we need. Coordinate system, that's fine, that doesn't do anything. And here mesh. I can create my mesh using the default parameters or the arithmetic mesh to see what we get. So I go to this option, so right click on mesh, then generate mesh. and let's see what happens. And we got this, which isn't that bad at all. So now let's play with the options on mesh. Element size. By default, instead of using elements, the default element size, let's make it 0.05. Okay, then generate mesh. All right, so now I have simply one element across the x-axis, so temperature won't change. I will keep the same temperature on the y-z axis, but temperature will change along the x-axis because I have different elements, and therefore I will be able to capture the heat that is flowing along this axis. Okay, so now that I have my mesh, I go to transient thermal. Here I got initial temperature, that would be my initial boundary condition. And under initial boundary condition, I have 22 degrees Celsius, and I will leave it like that. So that's gonna be my cold temperature TC. And now I have to define my boundary condition. So I will come back again to transient thermal. I will right click and then pick insert, and I can insert these kind of boundary conditions: temperature, convection, radiation, heat flow, heat flux. So I will pick temperature, and for temperature, it's asking me what geometries. So I want to keep constant temperature at the ends. So that will be at x equals 0 and x equals 1. So I will pick this one, press Control, so I can also select this other face and select then apply. And the temperature, the magnitude will be some hot temperature. So let's make it 50 degrees Celsius. So let's assume that our hot temperature is 50 degrees Celsius. So I have 50 degrees Celsius, and that's it. And I want to see how temperature changes with respect to time. Now, under solution, I can also right click and select what I want to monitor or what I want to capture. In our case, we are interested in temperature. So I will pick temperature. And now I only have to take care of the analysis settings, or in other words, my time step, as well as the duration of the simulation. So I come to analysis settings, and here I have these three parameters: number of steps, current step number, and step end time. My step end time is 1 second, but let's make it 10 seconds just to see what happens. So when I select 10 seconds, I notice that my maximum time step is 1 second, meaning that at least I will have 10 time steps during that period of time. So within 10 seconds, my time step at maximum will be 1 second. Remember that the ends are at cold temperature, so I'm gonna make my cold temperature, so it should be actually inversed. So my end temperatures have to be 22, or let's make it 25. So let's assume that our ends are 25 degrees Celsius, and rather our initial temperature is 50. So it starts with the hot, and the temperature should decrease as the time passes. Again, solve. Yeah, and let's check the results. So everything happened so fast that we already reached the steady state solution at a much lower final time. So now I'm gonna pause this. I will come back to the analysis settings, and instead of assigning 10 seconds for the end time, let's simply say that I want this to run for 1 second. Solve. Okay, now let's check temperature. Yeah, and now this looks much better. We can see here that the temperature in the bar starts red. So let me pause it. Let me play with this, and I will place it right here at time 0. So time 0, maybe we want to make this maximum time step even smaller so we can capture that. So instead of being, the simulation is for 1 second, now the maximum time step, instead of being 0.1 second, I will change it to 0. Oh, I have to change this program control to off, so I can modify that and make it 0.01. So okay, so that's 100 points. Solve. Okay, so now let's see if I can capture this better. So let us get back. Let me drag this to, I want to come to the, okay. Or if we want to check every single time step, another thing we can do is simply come to temperature, right click, and pick this option that says create results at all sets. Now this should create 100 temperatures. Yes, effectively. I have 100 time steps, so I can check each one of them. And if I want to be able to see each frame, then I come to solution, right click, and evaluate all results. So all of them get evaluated. Temperature T2. Yeah, so here it is because I wanted to get this. We can see here that this is temperature and this axis is time. So we're simulating this problem from 0 to 1 second. And it starts, here I have three different lines, maximum, minimum, and the average value. And here I also have this table. So when the simulation starts, what this means is that my minimum temperature is 25, which makes sense because I set the ends at 25. So it would be this end and this other end. And the maximum value should be 50 because that was the initial temperature, the initial condition. So 50. So everything in red is 50. And the average is simply the average of all these different values. Now, as time passes, we can see that we have time step 1e to the minus 2, 2e to the minus 2, and so on. Then the minimum temperature remains constant because we set that as a constant, but the maximum temperature starts decreasing. Why? Because in the physics of the problem, if I have my bar and it initiates at 50 degrees Celsius, since I am keeping these two ends at 25, then conduction heat transfer will make this object to find its final steady state, in other words, equilibrium temperature. And the equilibrium temperature or the equilibrium condition will be 25. So everything has to end up at 25 degrees Celsius. So the bar will start cooling down as time passes until the whole bar will be at 25 degrees Celsius. And that's what's happening. And as time passes, we see that that actually occurs. I can pause this and I can go and check every single time. So this is a temperature distribution at the first time step, the third time step, the fourth, and so on. And we see how temperature is decreasing very rapidly, in fact. Then the slope starts flattening, and of course, that would be the whole simulation. Now, by time, maybe up to this point, I believe that would be like 0.65, then the whole bar is at 25 degree Celsius. Now, what you need to do now is if I come here, because you're going to have to solve this problem on your own, you can obtain data from here, the different temperatures along the x-axis, and then compare that to your own solution. Okay, so let's save now this so we don't lose our project.